Thank you for the introduction. I am James Dong, and I'll be presenting my work on a compiler for fused relational operations on multisets. So first I'll give an overview of database systems, where relational databases are ubiquitous in modern software due in part to the flexibility of the relational model being suitable for many domains. Database systems take as input a query written in SQL and transforms it into a query plan composed of relational operators. For example, the query plan shown here is composed of a union operator on top, two joins below it, and a filter operation on the left. You may notice that this is not syntactically equivalent to the SQL query on the left, where the filter has been pushed down past the join as an optimization to reduce the amount of data processed. So after this query plan is constructed and optimized, the system then executes the query. Simple systems interpret these operators directly, but more sophisticated systems will perform some degree of compilation on the query plan before execution. We propose a system for compiling relational queries to fused code. Fusion here refers to operator fusion, or combining multiple relational operators into a fused implementation rather than materializing intermediate results. The two inputs to our compiler system are a query plan and the data structures to be used, such as the storage for the data structure, data tables, and indices. We obtain the query plan from a front end, which takes in the SQL query and produces an optimized query plan. The compiler system then takes these two inputs and produces efficient fused code. For many queries, fusion is necessary for optimal performance. The benefits of fusion are especially pronounced for cyclic queries, which show asymptotic improvements from fusion. The classic example of this is a triangle query shown here, where we have three vertices A, B, and C, and we join on the three pairs of edges between them. This query highlights a limitation of traditional query plans with binary joins, where a traditional query plan evaluates the query as a sequence of binary joins, each combining only two relations at a time. And no matter which two relations you choose to join first, the resulting joined relation has O of n squared tuples in the worst case. However, a fused multi-way join is able to achieve O of n to the 3/2 by simultaneously considering all three relations and avoiding the materialization of the O of n squared intermediate results. So two important lines of work in relational fusion are worst-case optimal joins, such as Ingno's work in 2014, and pipeline fusion as used in Hyper in 2011. Worst-case optimal join allows for fusion of inner joins, and it achieves optimal asymptotic complexity for the triangle join shown previously, as well as other cyclic joins. And in general, it can fuse any number of inner joins, as shown by the complex example on the slide, which has 4 different relations joined together. Fusion of inner joins, by the way, means simultaneously advancing through all joined relations, producing tuples as you go, and avoiding building large intermediate relations. On the other hand, pipeline fusion is restricted to only fusing a single pipeline, but is able to fuse together other operators than just inner joins. And so as a result, pipeline fusion is very good at fusing together unary operations such as filter and aggregation or group by, whereas worst-case optimal joins are able to fuse any number of inner equijoins. But there are many other operations that cannot be fused by these systems. For example, inner equijoins are only one type of join used by relational queries. In addition to inner joins, we have 3 other types of joins, left, right, and full outer joins, which are collectively termed outer joins. And non-equi joins, in contrast to equi joins, allow for arbitrary predicates as their join condition, not just attribute equality. Finally, we would like to support set operations, such as union and intersection. Our compiler system extends fusion to all of these operations in the diagram. Having a unified compiler for all of these operations requires a powerful compilation scheme where most of the complexity comes from these new operators. So let's look at the overall flow of the system using our compiler approach. First, the front end translates a query written in SQL into a query plan, where we do not implement this, and we assume that this is already present. Next, the compiler will lower this query plan into a new intermediate language, LAR, which represents fused operators as a series of nested loops. In order to compile these loops to native code, we first extract the loop domains and construct iteration machines, which are an auxiliary data abstraction used for generating fused loops. These are built on top of iteration lattices from Taco, and we generalize them to the expanded loop domains used in relational algebra with multisets. An additional input is the data structure specification, which specifies the data structure used for each input relation and the routine implementations necessary for code generation. Finally, given all of these inputs, the code generation algorithm will generate C++ code from the LR and iteration machines, along with the data structure specification. So our system has too many details to be covered entirely. So in this talk, I'll focus on the lowering procedure and how the complex operators are represented in our IR. For more details about iterations of machines, as well as the other parts not covered, please see our paper for more. So this talk is about compiling relational algebra. But another related algebra is tensor algebra. And let me talk a bit about the relationship between these two to get some key insights into our compilation approach. So on this slide, we have a few tensor algebra expressions. And here's part of the compute graph for attention. This is based on the IR used in JAX, where the top node here is a matrix multiplication, and the left node here is a ReLU. And here is a query plan for the left-hand relational algebra query, where there are some things that are similar between operators and tensor and relational algebra, where the structure of an inner join is actually very similar to the structure of a matrix multiplication. And so as a result, we could imagine using sparse tensor algebra techniques to compile relational algebra. And it turns out that this actually works quite well for the natural relational algebra, which is restricted to inner joins and sets, not multisets, without any complex operations. For example, this query on the slide here is in natural relational algebra, but the relational algebra in modern databases is not linear. In particular, suppose we change the join here to a left join, or to a non-equi join, or if we change the inputs to be multisets, where both of these modifications lie outside the scope of the traditional tensor algebra compilation techniques, where non-inner joins, such as left joins, require null handling, and multiset semantics changes the semantics of all operations and introduces some significant challenges to fused code generation. In order to handle the full generality of relational algebras used in real-world applications, we have developed a compiler system that is able to fuse all of these complex operations in a unified way. So let's look at how to represent an inner join in ALR. To capture the semantics of an inner join, we must first take the intersection of the b values in A and B. So this is performing the join operation. And the remaining loops will then extract the corresponding values of A and C from the A and B relations. Another key point is that these loops are abstract loops and are not tied to any particular data structure. For example, given the tuples for relation A, we operate using a coordinate tree that abstracts away the physical data structure. And if you look at the two attributes of A in the LAR, these two uses of A are linked, as shown in the coordinate tree. So as a result, the iteration of the second attribute, A.A, is restricted to only those values corresponding to the current iteration of A.B. And the coordinate tree abstraction is able to represent many types of real-world data structures, including row and column storage, tri-storage, hash tables, and B trees. Now, to represent outer joins, we require some new machinery. So let's look at how a full outer join is represented. The semantics of a full outer join, unlike an inner join, includes all elements from both joined relations, where the missing attributes, where no corresponding tuple exists, are filled in with null values, indicated by the empty set symbol. So to generate the ALR for this outer join, first we look at the semantics of the full outer join, and we take the union of the corresponding attributes. And next, the values of A and C should produce null values, where the B value does not exist in A and B respectively. And to represent this, we add a union with the null symbol, where the domain A.A union null produces a null value where B is not contained in A, and otherwise produces the corresponding values of A. We do the same thing for C, and we have the tuple generation unchanged. Now let's look at left and right joins. Like before, we write down the domain of B corresponding to the join semantics, where here we have simply A.B. However, the C loop should iterate over the C values corresponding to B, but the domain of B, if you can see, doesn't reference B.B at all, and so now B.C is not linked to anything. To fix this, we use the parenthesis operator to reintroduce B.B syntactically. This operator doesn't influence the actual domain of iteration, but it informs the code generator to insert branches to determine membership in B. Using this operator, we now see that the third loop, B over B.C, is now linked to B.B. As you can see, our approach uses simple loop domains that clearly expresses the resulting iteration behavior. This is supported by the linking behavior from the coordinate trees, which then ensures that the values correspond to actual tuples. Next, we'll talk about lowering. The input to our lowering procedure is a physical query plan. A physical query plan contains information about what implementation should be used to execute each operator. Our lowering process consists of rules for each operator, which means that the physical query plan specifies which rules should be used to lower each operator. We implement this by using a physical query plan with annotations. The perm rule at the top means to permute the loop ordering into a given new ordering, and the pre-comp rule means to pre-compute the given subtree into a temporary relation before proceeding with the rest of the query. We note that our work has fewer pipeline breakers, which require pre-comp annotations than hyper, but some operations such as aggregations remain pipeline breakers in our work. These pre-comp annotations, form an explicit fusion boundary, shown in orange, where the operators in each orange circle are fused together, but fusion does not occur across circles. As we'll see, the mechanism for fusion is accomplished by the lowering rules, whereas the decision of where fusion occurs is decided by the query plan. By performing fusion during the lowering process, we gain the advantages of both the high-level representation of query plan operators and the low-level loop representation without losing the benefits of each. On a high level, we have locality of annotations on operator subtrees compared to the global scheduling commands of Taco. And on a low level, we have greater flexibility since we have access to the low-level loop representation during lowering. Now let's see how our compiler lowers a query plan into LAR. We take as input a query plan with annotations that informs the lowering process, where lowering proceeds bottom up using lowering rules for each operator. Let's call the results of the pre-computed section T, and the rest of the query then uses T as a normal relation. We omit the lowering of the actual content of T for this talk, but iteration over T, where we just treat this as a standalone relation, this is lowered as shown, where you may notice that there's an extra dupes loop. This is covered in detail in our paper, but in a nutshell, it's used to handle multiset semantics in general. We proceed bottom up, so we lower the union of A and B, as shown here, simply taking the union of corresponding attributes. Next, we need to lower the top join operator, where going in detail, we are doing an inner join. So we first produce the join condition by taking the intersection of the corresponding attributes, which produces the domain shown here. Next, we copy the domains for the remaining A and C attributes. And for dupes, we take the Cartesian product, and this is according to the multiset semantics of join. Next, we merge the output tuples. Finally, there's a perm annotation on the top, and so we will apply the perm annotation by permuting the loop ordering. Next, let's look at the performance of our system. In this talk, I'll only cover a few of the key results on fusion, but our paper has several more key results, such as a data structure comparison, where here we have the results for the triangle query from before. So here we have input size on the left, on the x-axis, and runtime on the y-axis, where lower is better. And on this log-log plot, we see that our approach has an asymptotic speedup compared to the other systems which use binary joins. Next, let's look at the results from the LSQB benchmark, which uses a diverse set of operations, including cyclic joins, union operations, and anti-joins. And we see that for Q2 and Q4, we are roughly comparable to Hyper, which uses pipeline fusion, as well as free join, which is a relatively recent implementation of worst-case operable join. You'll notice that the Q4, there's a small caveat where, due to their output representation, they're not directly comparable. But in our paper, we have a detailed comparison where we show that we are, in fact, comparable. Q6 and Q9, where Q9 has a cyclic anti-join, and otherwise it's the same query, show significant speedups from our approach, where our compiler approach has the flexibility to reorder loops to defer iteration, leading to a 6 and 14 times speedup. Please see our paper for a more expanded evaluation, including TPC-H results and a data structure comparison. So in conclusion, we've shown how to fuse together these complex relational operators. And yeah, thank you for coming, and I'll open for questions.
Okay, again, thank you, James. And let's take questions up here at the microphone. Well, while people wait, I did want to know, can you expand a little more about free join? Why is the data incomparable, and what did it take to incorporate?
Yes, of course. So here, the free join essentially has what they refer to as a factored input and output representation, where essentially they factor like some amount of the multiset semantics. And so as a result, their output representation is also factored. And so they are able to basically completely skip the multiset semantics. And so we actually also implemented a factored representation. We show that our approach is very comparable.
Very cool.
Great talk. This is Yi Hong from UW. So I have two questions. The first question is, have you compared with Umbra, which is a successor to Hyper?
Sorry, which?
Umbra.
Oh, yes. We were aware of the system. We did not have time to implement a direct comparison.
Okay. My second question is, in my experience, worst case OpenJOIN usually spends most of the time in like building the indices. Are you doing something like fast for that, or are you
Yeah. So the results shown here omit all index building costs. Right? Okay. So this is directly the speed of the actual join implementation.
I see. And what kind of indices do you use in this?
Yes. We use essentially a tri-representation for most of the results. We also have an expanded data structure comparison in the paper.
Thank you.
Okay. Thank you again for James.